In this section, we're going to investigate the relationship between the hydronium ion concentration, or the acid concentration, and the hydroxide ion concentration, or the base concentration. To remind ourselves about the notation, when you see brackets like this, that's shorthand for the word concentration. And H3O plus refers to the acid. Now the second one, the brackets, again, always will mean concentration. And the hydroxide ion refers to the base. Now water does something called self-ionization. So if two water molecules react together, one can act as an acid and one can act as a base. There are chemicals that can act both as an acid or a base. And when water does that, it breaks apart into the hydroxide ion and the hydronium ion. So even in a neutral water solution, there is still some base present, hydroxide ion, and some acid present, hydronium ion. When a solution is neutral, which pure water would be, then the concentration of the acid and the concentration of the base are equal. Now it makes sense that pure water would be equal, because if we look here, for every OH we produce, there's a H3O plus. So they cancel each other out to make a neutral solution. So a solution that's neutral has both acid and base present. They're just in equal amounts. Now, when a solution is basic, it does not mean that there's only base present, but what it means is that the hydroxide ion, or the base, is greater than the hydronium ion. So that makes it basic, because there is more base present. And then following along a similar line, if something is acidic, it would mean that the acid concentration must be greater than the base concentration, and that makes it acidic. So in any given water solution, it's not that we have no acid or no base, but instead we have different conditions. So when we're neutral, it means the acid and base is equal to one another. When we're acidic, so this would be high acid, and this would be low acid. And then if we know that we also have base present, we have high base, which is the OH minus, and low base. And in the middle, they're equal. So if I go above, my acid is higher than my base, and this would be acidic. If I go down here, then my base is higher than my acid, and these guys are all basic. So we kind of have this sliding scale, and when the acid gets greater than the base, it's acidic. When the base gets greater than the acid, it's basic. Now, because water always has some acid and base present, it has an equilibrium constant that we call Kw. And Kw is equal to the acid concentration times the base concentration. We know that equilibrium constants will change with temperature, but if I'm at room temperature, the acid and base multiplied by each other always equal the same number. We can use this equation to help us calculate the different amounts of acid and base present in a solution. When a solution is neutral, mathematically, the acid and base are equal, and they both have to equal 1 times 10 to the negative 7. So a neutral solution has a concentration for both acid and base as 1 times 10 to the negative 7 molar. Now in an acidic solution, remember that the acid is greater. So the acid would have to be greater than 1 times 10 to the negative 7. So in an acidic solution, the acid is greater. But as a result, since it's a sliding scale, the base becomes less than 1 times 10 to the negative 7. Recall when you're talking about exponents that the greater the negative exponent, the smaller the number. Now when a solution is basic, remember the base has to be greater than neutral. So in that case, the base is greater than 10 to the negative 7, and the acid has to be less than 10 to the negative 7. Remember, when you have high acid, your base will go down, and when you have high base, your acid will go down. So here's a calculation that we can do, and after we've done this, we'll evaluate to see if our solutions are acidic or basic. So it says calculate the hydroxide ion concentration when we know the acid concentration. And I'm assuming all of these are at room temperature because they haven't said otherwise. So I know that Kw is 1 times 10 to the negative 14, and it will equal the base concentration times the acid concentration. So I'm trying to solve for this so I won't have it, but I can plug in 1 times 10 to the negative 14, which is a given number. This is Kw. It will always be the same. That will equal my base concentration times my acid concentration, which was given. So now solving that, and I'm just rearranging it over here, the base concentration is going to equal 1 times 10 to the negative 14 divided by 2.8 times 10 to the negative 10. Plugging this into my calculator, I get that the base concentration equals 3.6, and I'm rounding the coefficient to 2 significant figures because of this. 3.6 times 10 to the negative 5th m. And this is what they wanted me to know. Now the question did not ask me this, if the solution is acidic or basic, but I want to try to apply what we were talking about previously. So I know if a solution is acidic, the acid would be greater than 1 times 10 to the negative 7. And if it's basic, that's acidic. If it's basic, it would be less than that. So looking at the acid, I see that it's a negative 10. So negative 10 is less than 1 times 10 to the negative 7. So if the acid is less than 1 times 10 to the negative 7, then that means this solution is basic. You could also use the base concentrations. A basic solution should have a base concentration greater than 1 times 10 to the 7. And looking here, a negative 5 is greater, which confirms that this is a basic solution. So let's go ahead and look at the second problem. And this does a similar thing, except instead of giving us the hydronium ion, or H3O+, we're given the hydroxide ion, or OH-. So I know that these two numbers multiplied together at room temperature would be 1 times 10 to the negative 14. So this is a given equation right here. And so I know that 1 times 10 to the negative 14 will equal 10 to the negative 6 times the H3O+. So solving for this, so I have H3O+, is going to equal 1 times 10 to the negative 14 divided by 10 to the negative 6. Now, oftentimes, if you're going to enter this into your calculator, when you have a number like this, my calculator, I have to enter it in as 1 times 10 to the negative 6. Yours, you may not. And you should get 1 times 10 to the negative 8. The great thing about exponents is if the coefficients are both 1, all you have to do is subtract the exponents and you get the answer. So again, let's consider if this is the answer to the question. I apologize. And now let's consider if we think this solution is acidic, basic, or neutral. Well, it's not neutral because it would have to be 1 times 10 to the negative 7. So I know that if it's acidic, the acid will be H3O plus is going to be greater than 1 times 10 to the negative 7. If it's basic, the acid will be less than 10 to the negative 7. And I look here, and a negative 8 is less than 1 times 10 to the negative 7. So this solution is basic. I could also look at the base concentration, which is 10 to the negative 6. And that base concentration is greater than 1 times 10 to the negative 7, which makes it basic.